The applications from the previous video were primarily about setting up integrals. We're now going to see how we can use that ability to address more complex problems. The center of mass of an object can be thought of as the balance point of the object. For a circle, it should be intuitive that the balance point is right in the middle. But for a half circle, you can probably intuitively recognize that it's somewhere along the line that cuts it into 2/4, but where exactly along that line is not at all clear. This problem gets even more complicated when we think about objects where the density is different in different locations. In order to develop the formula for the center of mass, we will start with balancing two objects along a massless one-dimensional bar. The two objects have different masses and are located at different positions. In order to talk about these positions, we're going to introduce a coordinate system. How do we find the balance point? Let's call the balance point x bar, and we can intuitively see that it's somewhere between the masses. What causes the bar to tip? It turns out that this is related to the torque the masses create around the balance point as gravity pulls on them. If the sum of the torques is 0, then the bar will be balanced. Otherwise, it will tip over. And while we could go through this whole discussion using vectors, it's easier to note that when the force is vertical and the bar is horizontal, we can use that torque is equal to force times distance. The force is due to gravity, and the distance can be calculated since we know the positions. We'll say that the objects to the left of the pivot produce a negative torque, and the objects to the right of the pivot produce a positive torque. This corresponds to the right-hand rule. After some quick algebra, we get this equation, which gives us a strong hint for how we might generalize the situation. Let's do some quick algebra on the general form. First we distribute, and then separate the sum into two pieces. Notice that x bar is constant, so it can be factored out of the sum. Then we move the second sum to the right and divide by the first sum to solve for x bar. And this is the formula to get the center of mass for one dimension. How can we handle this in two dimensions? It turns out that we can view each dimension independently of each other. To find the center of mass in the x direction, we view everything from the point of view of the x-axis and reduce it back to a single variable problem. Another way of saying this is that we're creating a vertical line as a balance axis. We can do the same with the y direction. Then bringing those together gives us the full form of the equation for the center of mass. This is a good start, but we need to move from discrete masses to a continuous mass in order to determine the center of mass of a lamina. Fortunately, we've developed all the appropriate skills in the previous section, so we just need to apply them to our situation. Conceptually, we're just going to take our lamina and cut it up into a bunch of pieces, and then use our work with discrete masses. In the limit, as the pieces get smaller and smaller, we change the sum to an integral. The only trick is we need to think carefully about which part is cut up into pieces. In this case, the mass is the part that is being cut up, and so the mass becomes dm. This gives us the conversion for the various sums. But then we need to use the fact that the mass is related to the area element through density, which we can then substitute in. From here, it's basically just a matching game to get the center of mass. When it comes to working out these problems, it's mostly about keeping the computational mess organized. When I work on these problems, I calculate the mass of the lamina separately rather than putting it into one gigantic fraction. I find it makes my life a whole lot easier to not have fractions made out of double integrals. There are simply too many ways for me to make mistakes. As you do these problems, you can sometimes use symmetries to help simplify your work. While you should be able to grind out long computations, the use of symmetries is a way of learning to think ahead and work more efficiently. Sometimes you can use both a geometric symmetry and an algebraic symmetry together. If both the region and the density are symmetric about an axis, then the center of mass for the opposite axis is 0. The explanation for why it's the opposite axis is a bit wordy, but the pictures make this intuitively obvious, so it's better just to focus on the picture. Another type of symmetry shows up in the integrals. If your interval of integration is symmetric about 0, and the function you're integrating is odd, then the integral will simplify to 0. You can also separate out the odd parts of the integral from the rest of the integrand, which may help you to simplify your work. The common odd functions are odd powers of x and the sine function. Just be certain to double check the limits and check that the function is odd before applying this trick, otherwise you're going to make mistakes. But if you can correctly identify when this happens, you can save yourself a lot of work. So it's worth keeping an eye out for these things.